Happy Saturday and welcome to the second week of Science on Saturday. My name, if you haven't met me before, is Andrew Zwicker. I'm the head of public engagement and workforce development here at the laboratory, but most importantly, I get to be with you every week as the host of Science on Saturday, and I'm thrilled to see everybody. I know we have a few people who are here for the first time, and we have some people who we found out last week have been coming for decades, as it should be. If you are here for the first time, we've been running this lecture series here at the Plasma Physics Laboratory for over 4 decades. And the laboratory's been here 75 years, and for more than half of it, we've been running this lecture series. So just a couple of course, show you the pictures of that. By the time I get here, it's always gone. We're never ordering enough, so I hope you are sugared and bageled and cream cheese and coffee and teed up. Um, as always, we ask you to hold your questions until the end of the lecture. There are microphones. We're going to do something a little bit different just to try it. We'll have people running microphones, but if you would like to, you can easily get up and form a little queue and ask whatever question you want. And I know there are a lot of demos down here that you may want to see afterwards. If you're on Zoom, I'll be monitoring the chat. And if you want to put a question into the chat, I'll make sure to ask our speaker. If the fire alarms go off, there are obviously the exits out in the lobby. And if you want, there's also a fire exit here with some steps that go outside. So I don't know how to get that part of the Zoom away. It is my absolute pleasure to introduce you to Professor Aimy Wissa, Associate Professor of Mechanical and Aerospace Engineering at Princeton and co-director of Princeton Robotics. You can see her bio there, but she is an award-winning scientist, engineer whose work focuses on modeling and experimental evaluation of dynamic and adaptive bio-inspired structures and systems. I'm totally thrilled. I've wanted to do something around robotics and motion for quite some time. Would you please welcome Professor Aimy Wissa? But before you begin, I got to ask you a few questions. So we have a tradition here, most people know, but the same questions all the time. So would you share with everybody when you personally first got interested in science and engineering?
Sure. Welcome, everyone. Thank you so much. I'm thrilled to be here. I think I remember I was like 5 and I got my first airplane. My dad was traveling to Europe. I didn't grow up in the US, I grew up in Egypt. And my dad went to Europe for a work trip and he came back and he brought me an airplane. I think it was, and I think it was just, and I saw it and I think I didn't let it go for a while. I slept with it. I tried to shower with it. That was the hook. And from that point on, I was always walking, looking up. So yeah, that's how I started.
How about a teacher from elementary school to your PhD that, when you think back about it, really was influential on you?
That's I have to admit I had a preview of the questions and this is the hardest one. There was a couple I would call them like big turning points along the way. So um, math kind of became something that I really liked around fifth grade. Before that, I was something that I'm okay with, but then fifth grade I was like, okay, this is something I can hang out with for a while. It was my fifth grade math teacher. And then in undergrad, I thought I was going to go to industry and work at a big aerospace company. And then I went there and I'm like, I liked it, but I wasn't like, I thought, I thought I was going to it's going to be more, engaging for me. So I came back and somebody told me about this thing called research because I didn't know what it was. And basically they gave me a Dremel, an aluminum plate, and they put me in a lab and I looked at something called structural health monitoring and things didn't work at all, but I was having a blast. And I would come home at like 2 a.m. Nothing has been working all day, but I'm just so excited to come back. So that was the second turning point. So that was Professor George Lasser at Penn State, so university. Okay.
So when you're not doing engineering and research and teaching all the other things you do, what's something you do for fun?
Uh, my daughter's here, so I hang out with my kids for fun. Uh, no, I love swimming. I do some volleyball, and I just love hanging out with my family. So yeah.
And since last question, so this is the 75th anniversary of the laboratory, I've been asking everybody this year, tell us about the state of your field 75 years ago.
Yeah, so my field is broadly defined somewhere between aeronautics and biomimetics. So both fields in the 50s were super exciting. In the 50s for bio-inspired design or biomimetics, actually the term started coming around. There's been books that says how can nature inspire innovation. Of course, from before that, Da Vinci and all his works and inspired flight. But in the 50s, this idea of bio-inspired design started coming as actually like a method that people can start thinking about. And then, of course, in the aerospace side, just in terms of we were, after the World War II, and started thinking about pushing really speed, materials, and thinking about aircraft in a really interesting way, pushing really what we can do in terms of speed and materials and construction and things like that, and configurations. So it's cool.
And with that, Professor Aimy Wissa, Nature in Motion, Science on
Yes.
Saturday.
Awesome. So the first challenge is to know how to share my screen, which is usually not that of a challenge. Okay, perfect. Share. Right. Right. Okay. And can people on Zoom hear me okay? There we go. We did it. Awesome. All right. So today I want to talk to you about my passion. And they said hold questions to the end, and we're going to try to be rule followers, but we don't have to. So if you have like a burning question or something, and I'm going to ask you something, answer me back. But I just want to share with you something, the work we've been doing in my lab for the last, let's say, plus minus 10 years. Well, not, minus 10 in the last 10 years. And just share with you some of this incredible journey. So this journey would not be possible at all without, without, oh, sorry, here we go. Okay. Without sponsors, so people that fund our work, so industry, government, and Princeton Engineering has been really supportive. Our approach to these problems that you'll see, we'll see those three things coming together. I think a lot about biology and biomechanics. We apply different experimental analytical engineering tools, and there's a big element of design in the work we do. But really, this work is possible because a group of incredible and talented graduate and undergraduate students. They are the ones in the lab, they're the ones that do everything, and they're really the reason I love coming to work every morning, because I get to talk to them. So I call this the biology and engineering two-way street. And hopefully the last video show you that, and a lot of people are talk about this side of the street of how we can learn from biology to make engineering systems better. But I think actually that's half of the story and a huge missed opportunity. The other half of the street is actually we have something that biologists as engineers don't have, which is we can create very controlled experiments and develop models. It's like, when we have animals in the lab and we tell the beetle jump, it doesn't work. When I have a robot and when I plug the power, it jumps. So the idea of having repeatable, controllable experiments is something very powerful, because then you can test a huge parameter space and answer questions that sometimes are impossible to answer by observing the actual organism. And I'll show you examples of that. So, and the more I do this work, the more I really find that it's iterative. Sometimes you start by saying, I want to design an airplane that's as quiet as an owl. But then in the process and in building experiments, you find that actually, oh, that's what owls are doing. This is the new physics that I've learned that I'm now contributing. So it's an iterative, and you keep going back and forth. Now, people walk this two-way street in many fields. Some people will think about it in terms of material design. Some people will think about it in terms of, computer networks. Some people will think about it in terms of materials. My group think about it in terms of locomotion. So at the Bio-inspired, I lead the Bio-inspired Adaptive Morphology Lab, and we think about bio-inspired movement and locomotion a lot, the kinematics piece is the movement piece. So part of our lab, we work on bird-inspired flight. Part of our lab, we work on insect scale dynamics. And part of the lab, we think about multimodal locomotion. And the tools we apply, if you say, okay, what classes, Amy, I want to come work in your lab. What are the classes I should take? Well, I think you should think about fluid dynamics because we think about flight and swimming a lot. You should think about structural dynamics because we think about how things move and bend and twist and things like that. And biomechanics because we have to understand how, morphology in terms of muscles and tendons and things like that translate into producing forces and motion. So you put all this together, and we are able, because of the combination of these tools, we're able to study bird-inspired flight, insect scale dynamics, and multimodal locomotion. And what's something that I think about a lot is, okay, fine, biology and engineering together in this big theme of bio-inspired locomotion, what do you learn? The first thing, actually, and it's interesting, you learn these actuation and locomotion strategies. How should I move? Where should I put like a motor? What should I sense? Things like that. On the other side, you can learn control strategies. And what's interesting, unlike a lot of the robots that we build, we rely a lot on having like a sensor, an actuator, and the sensor senses something, and the actuator responds, and there's a controller in the middle. But nature or biology, and especially like birds, for example, they respond to things in a passive way, a reflexive way, and an active, so different levels of control. So just today we're going to talk about, and we did this for my lab for many, many systems. For the sake of time, I'm going to just talk about these three. And I have more about the other system that I haven't studied down here at the end. So are you ready? Let's do it. Let's do it. Okay. So let's start by click beetles. How many people played with click beetles or have encountered click beetles? Okay. It's too cold for them now, but in the summer, if you see one, pick it up. It's so cool. And and if it's not a click beetle, if you pick something by mistake, it's not my fault. All right. So now let's play another game. Okay. Tell me when I say think of the fastest animal. What do you think? Yeah, these are yesterday news. So cheetahs, I do this because it works all the time. Cheetahs' accelerations are 10, 15 meter per second square. You know who are the acceleration specialists? The small animals. Frogs, fleas, grasshoppers, click beetles, mantis shrimp, trapjaw ants. Sorry. Okay. And why do they do this? For example, a trapjaw ant that's producing millions of meter per second squared. Millions, okay? They close their mandibles really fast at 10 to the 6 meter per second square to escape or to catch a prey. Mantis shrimp, they have these clubs that they're able to basically use to open shells. It's so powerful that they create cavitation bubbles underwater. All right? And click beetles, which we'll talk about now, they do this really interesting no legs fast sit-up, and we can practice after the lecture. We're all laying on the ground, we'll do fast sit-up. But they can do this really fast sit-up, and they can launch their whole body, many, many body length, her whole body, maybe 20 body length of their own body length. So imagine if you jump with no legs on the ground, do a fast sit-up, and you launch yourself, 20 times your body length. How they do that is actually very interesting, and I want to talk to you about it, but I want to tell you a little bit about click beetles. They come in all different sizes. The ones in the US, they're as big as my thumb. There are ones in Asia that might be a little bigger, but this is a beetle. And if you ever picked one up, you'll see this person trying to squeeze the beetle, but the beetle keeps clicking and it gets out of their hand eventually. And then it jumps away, right? And when they do this on the ground, like I showed you, they would do this really fast sit-up, and for small beetles, it can go up to 20 times their body length. Now, how do they do this? A cheetah, because when you guys were right, they are fast and they have high acceleration, but they can pack a lot of muscle, all right? Those insects and arthropods, they're volume constrained. They can't pack that much muscle, okay? So what do? Well, they do exactly what we do when we launch a bow and arrow. They use this strategy called latch-mediated spring actuated. So if you think of a bow and an arrow, your hand is the latch, okay? And your muscle, the motor, puts energy into the bow by your hand is holding on. Then the spring, which is the bow, stores that energy, right? So the energy goes from your muscle to the bow. And then when you let go, you break the latch, the bow recoils, and that recoil causes the arrow to release at much higher acceleration than it would, or much higher power than you would have thrown by your hand. Okay? So when we started this project, we knew that for the click beetle to be able to produce these high accelerations, it had to be the latch-mediated spring actuated. They don't have enough muscle to reach these accelerations just by direct actuation. But there was very little known about what's the latch, what's the spring, how's the recoil happening. So we started thinking about doing some experiments on actual beetles. And as an engineer, let me tell you, that was fun. And it took a while. I have a lot of insects in my lab now on purpose. And it's been joy. But, it took a while. So we knew that if you have a click beetle, and if you damage this hinge, it can't click and it can't jump. So what we did is we took the beetle, we put it in wax, and then we went to Chicago at the Advanced Photon Source, and we filmed them at 50,000 frames per second under X-ray. And we started looking at what does the hinge structure look like. And so you have a peg. You find that the hinge has this peg and this lip that sit right on top of each other. There's what we think are the springs, but we didn't know at the time. And there's a cavity. And the X-ray videos and pictures will look something like that. So I'm hoping you can draw some parallels. Here's the peg, here's the lip. This is one of the springs. And then we started saying, okay, let's see how these things work in action. So in the X-ray, the first thing we saw is the latching. That's your hand holding onto the bow, right? So we find that the beetle lifts its peg that then sits on the lip. Okay, that was the latch. We discovered the latch. And when we did ESCN, this is microscopy, we took pictures now back in the lab, and we found that actually if I had 10 beetles from different species, and I took off their pegs and their lips, and I kind of threw them on a table in front of you, you'd be able to match them. It's almost like they're like, and they look very different, they come in different shapes and sizes, but you would able kind of to match them like, a matching game, because they have to be conformal. So it was a geometric latch, that's what we found. So that's what the video is showing, right? The beetle starts like this when it's relaxed, and then when it's about to click or jump, the first step is it goes into this latch state. Okay, so now it's latched. What happens next? So you'll see it. It latched, then a muscle starts loading that bow, loading that spring. So here it is. You'll see it. The peg sits on the lip. Then this starts to load and load. And if I show you the time scales, this is how long it takes to load, about 146 milliseconds. This is how long it takes to release. All right, so energy is conserved. Power is energy over time. If I am storing energy at hundreds of milliseconds and releasing it at 0.8 of a millisecond, what I'm doing is I'm amplifying the power output, right? Power out is more than power in, not because energy is not conserved, but because I have two different mechanisms of storing this energy and releasing it. One relies on direct actuation of the muscle, and one relies on elastic recoil. So that's what these animals do to be able to say, use their small volume of muscles to get a big power output. And we thought we were done. We figured we went to a home, we got the spring, we're good. And then we're like, but wait, another student joined my lab. She's like, I think there's another spring. I'm like, what? So we did CT scans, and this is the peg and the lip I showed you. But on the back side, or the ventral side, you'll see, actually this is the dorsal side, you'll see that there's this orange element called a mesonotum, and it looks like a saddle. And if you look at the X-ray, and this is harder to see, but if you track this distance that here with the black arrow, you'll see that it's basically contracting. But then all of a sudden, so it takes, let's say, I don't know, what's that, 0.1 second? So 100, again, hundreds of millisecond, 100 millisecond for it to contract. But then after it contracts, if you zoom in this area, you'll see that there's a release, a really fast release. So it acts like another spring, almost like a poppet, like, you know, the things we put in our hair that goes clip in and out. It just, the idea is this is slowly contracts and then pops. So it's another spring. So it's a system of distributed springs that's been packed in this millimeter big beetle that allow it to amplify what a muscle can do. Amazing. It's just an amazing actuation strategy. And if you're a fan of big numbers for small things, after the spring recoils, the head, you'll see, the head will keep, you know, oscillating back and forth, and the peg will go back in and out in the cavity. The video will play again in a second. Here we go. And if you look at some of the acceleration produced on some of the body parts, 300 Gs of acceleration. Okay? So many questions. How does it not get damaged? What is the material properties? You know, all that is really interesting to see. So in summary, I showed you that we discovered the latch, that there's actually a system of springs, the mesonotum and the prosternum and the soft cuticle, and actually a system of muscles that are in charge of all that, but we didn't talk about the muscles. I'm happy to talk about them later. And it was really interesting, but you know, there's so many beetles. They only appear once a month, in the year, July and August, that's when we get, and then we have to get in the X-ray, and there's so many questions, like I told you. So as an engineer, I wanted to develop a tool that can help us answer more questions, like one that's showing on the screen here. How do you investigate how these components, like variation in these components, and like if you make the mesonotum bigger, does it become a better spring, a worse spring? And even if it's outside what biology can do, that's fine. I'm learning how to make, you know, robots for engineering. So we started by making something. I want to introduce you something that's, I think, very interesting, something called a robotic model organism. It's building a robot, not for it to jump or, you know, that will happen, but it's a robot that's designed to answer questions about biology, specifically about how do beetles do this, how do birds fly that way, how do, you know. So we started very simple. So again, a robotic model organism. There's a lot of echo. A robotic model organism. And for the beetle, that means it has to latch. It has to be able to convert some actuation into some desired, in the desired kinematics of loading and release. And it has to be able to store this energy and release it. And we started very simple. And I think this is really important for people in the room that are thinking about what is it like, you know, to think about how simplicity is key, and it's a good thing. Starting with some simple engineering models or systems to answer questions is actually a powerful tool. There's power in simplicity. So we said, okay, the first thing it needs to do is that it needs to latch. So we know that this is the latch. So we started saying, okay, let's look at the geometry, the key parts of the geometry, and make a latch that consists of a peg and a lip. So that was the first step. Then we said, okay, how does it need to move? So we started by looking at the video that I showed you and analyzing the degrees of freedom, the ways the system can move. And we found that there's a couple degrees of freedom. The first thing it needs to do, is you'll see that this peg actually rotates. There's a little bit of a delay. So you'll see that the peg, the blue part that starts this way, it actually rotates. Once it becomes in contact with that, it rotates. So that's one degree of freedom. Then we found that you'll see that the mesonotum, the other spring, this one doesn't just contract, it contracts and rotates. So there's 2 degrees of freedom. So you'll see it here, contract and rotate, and there's another, so that's another 2 degrees of freedom. So we wanted a total of 3 degrees of freedom, okay? So what we did is we started adding 1 pin joint here that would allow just for pure rotation. And then we added a pin in a slot here, a pin in a slot here, and that allows us to translate and rotate. So just like the hinge that's able to do these 3 degrees of freedom, our robot can do this 3 degrees of freedom. The last thing is this doesn't store energy, right? It can latch, it can move the same way, but it can't store any energy, right? Because all of these are like, so we added springs. And where did we add them? Well, we added them where the mesonotum and the prosternum would be. So we added a torsional spring here, and we added a linear spring there. Now let's see, did we get something that would be interesting and do the same thing? Just to remind you of video, this is the whole motion of the click beetle. So latching, loading, release. It's latched, you'll see loading, and then release. So now this is at a much larger scale and slower because we didn't think we're not matching mass or inertia yet, but we can still answer questions about what should be stiffer. Should that spring be stiffer or should that spring be stiffer? How does the stiffness of these two things relate to one another? How does it affect the motion, the latching, the loading, and so forth? And one of the interesting insights that we got from this is, if you look at, this is our one of the RMOs that we have. I don't know if you can see it okay, but if not, we can talk about it afterwards. But we found that the loading direction matters. I'm doing it with my hand now. But if you load in one direction, it releases prematurely, or it doesn't release at all. And if you do it in the other direction, you'll see that it latches, loads, and then release. I know that probably is hard to see, and I can show you. But we found that if you want to put an actuator on your robot, that's the line of action for the actuator. And guess what? It was the same line of action for the muscle that we observed in the beetle. So we now understand that the muscles and how you attach them in the beetle and in the robot are showing us similar insights, and that they matter. So that was an example of how this two-way street of biology formed, right? The tools we applied were imaging, experiments with high-speed, like light imaging, X-ray imaging. On the engineering side, there was lots of prototyping and different models that I didn't talk about. And now, this is our robot. And you'll see that's a lot simpler, and we're adding complexity, but it's doing the same thing I showed you in the beetles doing, this legless jumping. Where would you want to use that? Well, can you think of planetary exploration and it's going on a planet? A lot of times space missions stop not because a robot or a rover, the sensor broke, but sometimes it's stuck somewhere, right? And this can help you get unstuck, right? It can jump out of places. And the other thing, and on Earth here, they have to be pretty small because there's a reason why we can't do this legless sit up, right? And beetles can. But if you're able to play with gravity in space, maybe that's something you can use, and you don't have to be that much mass constrained. All right, from the ground, let's go to sea. Are you ready? Did I lose you? All right. All right. Who has ever seen flying fish in real life? Okay, I'm jealous. I thought they were a fiction. Like when my students showed me a video, I'm like, this must be fake. They're incredible. Flying fish, y'all. I don't know why I said y'all, but I felt like y'all. All right. So they're fish, they swim, but then when they're attacked, they're schooling fish. When they're attacked from the bottom with a tuna or a marlin, they'll do this incredible feat. They get out of the water, they deploy their fins, these big fins, and they glide. But you know what's even more wild? Sometimes they don't take off right away. Sometimes they keep their fins dipped in the water. They use the water as a runway. They flap their tail really fast until they gain enough speed to then glide and take off. Crazy, right? Okay. So here's what, let's take this and break it into bite-sized locomotion or motion strategies, right? So from the beetle, we learned an actuation strategy. How if you're small, you can pack enough power. From the fish, let's learn a locomotion strategy to be underwater and to be able to swim and fly. So they're fish, they swim like fish swim. Then they come out of the water, they deploy these really large pectoral fins. Then they do this taxiing maneuver that I showed you, where just the tail is dipped, they flap, and then they gain enough speed, they take off and they glide. Okay? Now, long you think a fly, they don't produce thrust, so they're not flapping, they're just gliding. How long you think in distance a flying fish can glide before going back and swimming underwater? Say a foot, okay. Other numbers. Couple 100 feet, okay. 20. 300 meters? 300 feet. Okay, so like about 100 meters. I think I did the conversion right. Are you guys ready? Hold on to your seats. Half a kilometer. Okay, that's, let's say 500 meters divided, that's like about 1,500 feet. Okay, right? Yeah, about 15, yeah, in meters and yards, let's say are the same. How do they do this when I just told you they don't produce thrust? Because they do something wild. They do this. They taxi, they glide for about 10 meters. So you guys were close for about 10 meters, so 30 feet, right? And then when they lose their altitude, they dip their tail again, taxi again, take off again. And they do this, they recorded one time, they did it 40 times. So you get this 400 meters or almost half a kilometer. And then when the threat subsides, they go back in the water and they're back to being fish again. Okay? Now, if you put on your biologist cap, and let's say we all go on a boat field trip to measure the kinematics and how they move and how fast their tail is moving and all this stuff, okay? And it would be very hard, right? Would you set your camera under the water, above the water? How fast is the fishes, like the boat is going? Can you track one fish because it's going to be really fast? So it's actually hard. It's really hard to do these experiments on actual fish. And this is a collaboration with a fish biomechanician and NJIT Professor Brooke Fleming, and she confirms, so it's not me being like dramatic. So, but before I get into tell you how we study them, and you can guess robots, I want to show you some of these key features that we're going to talk about. Their body is streamlined. They have this tail fin called a caudal fin, and it's asymmetric, and this is not common. Most fish will have a tail where the top and the bottom are symmetric. Sharks have the opposite, where the top in some shark species are longer. But here the bottom, and I'll show you better pictures, is longer for flying fish. Okay? And then they have these huge pectoral fins. They're really big because they turn into wings. And like I said, it's really hard to study them in nature. So what we did is we designed a robotic model organism. And you'll see we made this really interesting tiered shaft. It acts like a Kamen follower for those who are like machine lovers. And the way we do this is really important. This idea that it's a tiered shaft is really important because it gives us the right kinematics. It's not abrupt. It's like a continuous. If you look at the fish, and I have the robot here. Let's hope. I'm being super brave today with the demos, but if I crash and burn, I know you guys, it's all in the family. All right, Okay. All right, let's see. Uh-oh. It's cute. But this tiered shaft, and I'll show you a video for those on Zoom, but you'll see that the body kinematics, it's not abrupt, right? You can draw like a nice smooth curve at every point along, right? And then this is the tail that I told you is asymmetric, and this is to scale actually those pectoral fins. So a fish this side would have pectoral fins this size. Okay, you have a question? I didn't plan that question. She asked, why is the bottom longer? This is what I'm going to talk about. Thank you. But okay, so all right, so we use this robot. We developed this robot. And the point of doing it is to include features like the pectoral fins, the caudal fin, the steered shaft, so it drives the caudal fin at the right kinematics. And then again, the idea is to create this controlled, engineered experiments and examine a large parameter space that allows us to learn about. There's a lot we don't know about how these flying fish do this. Like, this is a lot of open questions. I'm sure you're gonna have a lot of questions, and my answer would be like, I don't know. But I think that's exciting. So I'm going to give you an example. You asked many questions. We've answered several of them. I think this is the one that is my favorite, so I'm showing it, is why is it asymmetric, right? And asymmetric in this way. Um, so we had because we're scientists, we form hypotheses. So our hypothesis was this uniquely elongated lower lobe has to help with taxiing, right? Because there's other fish that swim, right, that don't have it. So the thing that's really unique about the flying fish is taxiing. So it has to have a role during this taxiing maneuver and actually a transition, because this transition between swimming to taxiing is important. So what we did is we went in the lab, and this is now the robot in the water. And here's the whole picture of the robot now in the water channel in Princeton Engineering Quad with the water flowing over the fish. And what you're seeing here is the setup that we had. So we put the fish on this stand. We're able to change its pitch angle, so the angle of attack of it with respect to the incoming. We're able to measure the forces, control the depth, and we test at a Reynolds number or at speeds and scales that are relevant to the fish. And then we have a robot with an asymmetric fin and a robot with a symmetric fin. And what we found was really interesting, okay? So this is an experiment during swimming. So the robot is flat in the water tank like this, and again, incoming water flow. And what you're seeing here is we measured forces in the thrust direction and in the lift direction. And then this is basically combining these to see the direction of the force. And you'll see that for the symmetric fin, the forces are all over the place as we change the frequency of the we flap slow, we flap fast. The faster it is, the more green it is, and the vectors are all over the place of the forces. This is the direction of the force. For the asymmetric, all of them or most of them are aligned around the 30-degree angle. And if you're a fish that's swimming, what would this direction of force help you do? Get out of the water, right? Get out of the water. Not only that, it's at 30 degrees, which is the recorded exit angle of the fish. Okay, that's pretty cool. Okay, so what happens now during taxiing? So we changed the experiment where we mounted the fish at this angle and only the caudal fin is dipped in the water. And here we asked another question. There was work in the literature that was suggesting that the fish has to really control how much the caudal fin is dipped in the water. But if you're a fish, embody your inner fish, okay? If you're a fish or you're a controls engineer, whichever feelings you want to embody, it would be very hard to control how much that fin is dipped in the water, right? Like that's such a hard control problem, especially if you're swimming in open ocean, right? These are open ocean fish. But maybe it's worth it. Maybe if you have the right height, oh, it's worth it. Or the right depth, it's worth it. So we did that. We tested different depth, right? Not in the water at all, fully in the water. And this is the thrust coefficient, right? And what I want you to pay attention the most in this curve is how bundled they are for the asymmetric fin versus not bundled in the symmetric one. So for the asymmetric or for the non-symmetric one, they're bundled. What does that mean? Well, that means that if you're a fish with an asymmetric tail, you don't care that much about how much your fin is dipped in the water. And that's a feature, not a fault. Because guess where they swim? Well, they swim in the ocean. And oceans have waves. Aren't you guys excited that you came to the lecture? Ocean have waves? Yeah. So, so my point is, this asymmetric fin makes the flying fish less sensitive to changes in the wave height, allowing them to do this maneuver or this idea of taxiing and translating, repeatedly in different conditions. And while this lack of sensitivity to height, they maintain this idea of being, of the force vector being out and up to help them transition. This is a video I want to show you. This is what, all of the videos I showed you earlier, these are videos from BBC that they took days and days and days and out in the sea recording this is my student on a tour boat in Catalina, and I think the power of this video is just to show you how fast they really are, how hard it would be to actually, to go on a boat and this was the taxiing. Isn't that cool? You'll see it again, it plays again. But yeah, so they're so small, they're very fast, but they're incredible. And hopefully I showed you that flying fishes, and they're the only marine animal that can do this. They're the only flying fish, about 27 or 35 species. They're the only marine animals that are able to do this. And you need all that. You need the asymmetric caudal fin, you need the enlarged pectoral fin. And they're very hard to study, but hopefully today I convince you that robots is actually a really cool tool for studying nature in both of these previous examples in my talk. All right, we have some time. We have like 10 more minutes. So I want to show you now the opposite side of the street. Can we learn from, can we go to the, and this is, okay, this is, can we learn from biology to make engineering systems better? So I play this game and I want to continue play. When I say wings, I want you to say multifunctional adaptive structure. All right, we're going to do this together. Okay, wings. Okay, my favorite crowd. Usually you have to do it twice. We don't here. So when I look at a bird wing as an engineer, I see this system that provides lift, thrust, thermal insulation, sometimes attracts mates. You know, the point is, allows it to fly in adverse conditions during gusts at high angles of attack, when there's wind, when there's not enough wind, right? To perch on a tree, all the things that birds do. If you now think of an airplane, we have an engine for thrust, a wing for lift, flaps for control. So that's what nature really thrives, the multifunctionality. Yes, I can make a wheel because nature can't, and a wheel is maybe might be better than whatever nature does, but it turns, and that's about it, okay? Compared to multifunctional solutions that nature provides. Okay, so let's go. We're not gonna play this game again. The other thing I want you to think about when you say feathers, right? I want you to think about flow control devices, devices that can shape and change the wind over the wing. Okay, giving the bird an extended flight envelope. The same bird that you see, think of a falcon, think of a hawk, it's flying between trees, but it's staying up higher and observing, and then it dives really deep, okay? Feathers, we think, is one of the tools that birds use for that. Today I want to talk to you about this specific group of feathers called the covert feathers. We've been studying them for a while, and the more I study them, the more, like every time I think, okay, we're done, we learn something new. So they're contour feathers. They're on the bottom and the upper surface of bird wings. They give the bird wing its shape. That's why they're called contour feathers. They cover the flight feathers. And in biology, actually very little is known about their aerodynamic function, but we know when they deploy from biological studies. So we know they deploy during high angles of attack. So when this eagle is coming for a big landing, you'll see these feathers pop at the bottom and at the top. There's actually multiple rows of them. So it's not like one feather that pop. Many of them pop along the wing in both directions. And then we know that when they deploy together on the upper and lower surface. And we also know that they pop or they deploy when there's gust. So there was a study where they put a little camera on the back of an eagle, and the eagle took off from a cliff, and it was windy that day, and the feather was like pop, 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 pop. It was really cool. So now, as an engineer trying to understand how I can use that to make my airplanes better without plucking feathers and glue them onto airplanes, I have to simplify this system, right? So we start like really simple. We start by just a wing with a flap, and then maybe a wing with many flaps, and then maybe a wing that has something on the upper and lower surface, and maybe something with during gust. For the sake of time, I'll just show you for the sake of time, we'll just talk about the first two. Okay, so this is really cool. This is actually out right here in Forrestal campus. This is my wind tunnel. These are two people for scale. And we use this to put wings in wind flows similar to what they encounter when they're flying. We go to 0 to 50 meters per second. It's really cool. We're able to put wings or wings model. You make them from 3D print them, and we attach them to a force transducer so we can measure lift and drag. And then we can switch how the wings look like. We also have lasers and cameras, and that allow us to see how the air moves around the wing. So here's a video. Okay. Here's a video that's showing what you can get if you have a laser and a camera over a wing, right? So these little lines are velocity vectors. This is called particle image velocimetry. And what we can see is how air moves around. So blue means air is turning one way, red means air is turning the other way. These are called vorticity fields. And you're able to see how the wing changes. So I'm going to show you here in the next slide. These videos are pretty heavy, so hopefully they play okay. This is a lift curve versus angle of attack. Angle of attack is the angle of the wing along the wind, with respect to the wind. And this point right here, if you look at the blue, just a regular wing, you get lift increases, and all of a sudden this point happens where stall, where they basically you've heard about airplanes stalling and losing lift and crashing. That's what happens. So post-stall, we have this green line and orange line, so a flap near the back of the wing versus a flap near the front of the wing, and there's this stall improvement, lift improvement during stall. And even though the improvements are kind of the same for most angles, they look, even if you look at this angle where things are pretty similar, if you look at the flow fields, so this is the first video. Oh, it's not playing. Okay. Okay. The important ones are playing, which is good. All right, this is what happens when there is no flow over the wing, when there's no flaps over the wing. Here you have a flap near the front, and here you have a flap near the back. And notice something. The flap near the front of the wing is barely moving, even though it can do whatever it wants. By the way, there's no sensors, there's no actuators. It's basically a piece of plastic glued to the wing. The air starts turning, and then the flap deploys. The leading edge one is barely moving, but the trailing edge flap is moving a lot. Okay? And I can play the video up top. So they're doing something very different. And actually what they're doing is really interesting. This leading edge flap is bringing this separated flow near the wing surface. So if you look at the back, this is called the wake. The bigger and messier it is behind the wing, the more the drag. So this one actually makes this width, if you will, smaller. So it reduces the wake size. This one is doing something different. The wake size is similar, but it's creating a pressure dam that prevents this messy air from propagating all the way to the leading edge, maintaining lift production at the stall. So we did next for this, I want to show you something cool. Now we said, well, one flap works. How about 5? So we put more flaps, and birds have about 3 rows, and they're all near the front. But as engineers, we're not limited to that. We can put stuff during the back and see what happens. So here's a video showing the wing. I basically taped down flaps 1, 3, and 5 and allowed just 2 and 4 to respond. And that's what it would look like. And what I want to show you next is a couple cool things. So is this going to play today? This one is really refusing to play, but I'm okay with that because it looks exactly like that. Okay, this is the one I showed you before, and here's the wake size, right? So this is, we're going to call that the wake, the deficit, but this is the wake size. With one flap, I showed you that this wake gets smaller. Do you guys see that? Okay, now are we going to put all 5 on? What? No, I wanted this one to play. Okay, you can't. It's not playing for some reason, but hopefully you can see that it's a lot smaller, right? And what's interesting is you'll see that this flap interacts with this shear layer, the separated flow, bringing it closer so the second one can touch it, and then bring it closer, the third one can touch it, okay? And then the fourth flap, by the way, it can deploy if it wants to, but it's not deploying. You know why? Because the last one is deployed and it shields it because of this pressure dam. Basically, there's nothing making it deploy, okay? Now, how does this affect lift? Whoa, very bio-inspired. I love it. The blue is with no flaps on, the brown with all flaps deployed. Check this out. Remember, this was called stall with the sudden drop and lift? With the flaps on, there's almost no drop and lift. Continue plateaus. Okay? And we get that, and we reduce drag. So you get a lift benefit and a drag benefit. That's aerodynamic efficiency at really high angles of attack. Airplanes won't dare to fly at these high angles of attack. Well, the commercial ones, because you guys are on board. Okay? So because of stall, all right? So very cool. We have flaps that, mitigate stall, improve lift, reduce drag. is this too good to be true? Is this like something that we can actually put on an actual airplane and get benefits? Well, let's hope so. Well, let's hope this video plays. Videos are not incorporated with me today. No. Okay, this one will. So we put it on this airplane. I don't know what's happening today. We put it on an airplane. If you see this, this is actually a runway out here in Forstall. There's a little helipad. And we put those basically pieces of plastic. They weigh less than 1%, less than actually 0.1% of the aircraft weight. They're very negligible weight. We put them on, and then we took off, and we have a GoPro. And the GoPro is right on the wing, and you see the flaps are deploying. And what we do is we put the aircraft in something called a power on-stall maneuver. So we say, maintain altitude, okay, but slow down. So the aircraft has to pitch up, because that's the only way it can produce enough lift. It does that until it stalls, okay? And we measure what's the maximum angle we can get to before we stall. And if we have those flaps, those pieces of plastic inspired by feathers on board, we can reach higher angles before we stall. And when we stall, it's a lot smoother, because when we stall, our roll rate is a lot small. This is smoother. So these flaps really increase the maximum angle of attack and soften the stall behavior like we saw in the tunnel. So now that it did this, we said, can we go beyond biology? And I want to be respectful of time. So I'll show you a cool video, and then we can, because I want to have time for you guys to ask questions. So we got approached by a company, Toyota, and they want to design these kites that allows them to fly, to harvest energy, not using wind turbines, but using these kites that basically fly at much higher altitudes because the wind speeds are faster. And they said, can you help us? We have some problems with this kite. This vision is really good, right? Let's go harvest these really fast speeds so harvest lots of wind energy, but we have some problems. And what's their problem is, and we can talk about the mechanism of how we do this, but the challenges they had in flight was they crashed sometimes. Yep. And then sometimes what they had is because it's such lightweight, it's an inflatable structure, what they had sometimes was you won't be able to see it, but they have these really large oscillations, huge pitch oscillations, because the kite would just basically start pitching up and down like crazy until it crashes. So we put, and the question is, can we use the coverts to make their kites better? So we took the kite, we installed our flaps on it in the leading edge on the upper side and the lower side. We connected them with motors so we can actively actuate them because we want to use them also for roll and yaw control. And a couple years working together, we are able to have this very controllable flight. This is showing the pumping cycle, which is what you need to do to produce energy. And if this video plays, I'm going to be so happy. Maybe it'll play here. Yeah. So what you're seeing is huge pitch oscillation that I told you about before. And then the flap deploy, and then it stabilizes. And you see here with the data, like the orange is the pitch data. So you'll see that the oscillations grow and become very unstable. So then we deploy our flaps, and then the pitch oscillations die. So overall, we were really successful to translating what we learned, now it's working, to translate from in biology to very idealized experiments all the way to things that actually is useful in terms of harvesting energy or flying and minimizing stall. So at the end, I want to thank you for being here. And I want to, hopefully today I convinced you that biology and engineering form a two-way street, and we can learn from biology to make engineering systems better, but we can also use engineering systems to understand biology better. And I've showed you 3 examples today, but we have this amazing ecosystem in the lab where we think about things that crawl, things that glide like grasshoppers. You've seen about the beetle, and I have some cool stuff to show you about, things that we didn't get to talk about today. So with that, I would love to take questions.
So we're going to pass mics about. There's also mics here. So if you feel like getting up, please get up. Otherwise, we're going to pass the mic off to people as well. All right, so raise your hand. Sure, go ahead. Little switch.
Test. Okay, so I just wanted to make a quick comment that I've seen the flying fish at Catalina Island,
Yes.
and they would fly up on the deck of the boat. So they're
Yeah.
getting way out of the water. Like,
Yes.
yeah.
Yeah, and it's interesting. Some of the things, you know, there's the rest of the video that I showed you. It shows that the flying fish, they get out of the water to escape this marlin, and then they fly too high that a seagull eats them. So, but yeah, so sometimes I think where they exploit being next to the water because of ground effect, but they can reach really high.
Yeah.
Yeah.
Thanks.
No problem. Yes.
Hello. I have a question related to bats.
Okay.
It's one of the things I know about, it sounds like some of the similar technology with regard to drone bats, but there's also a lot about bat communication.
Mhm.
And you work with communication with any of these animals you're studying.
We're thinking more a lot about the locomotion and the mechanics, but I do have colleagues that think a lot about echolocation, and they think about how can we understand how bats communicate with one another. Like, for example, one of the things they do is they try to basically put the bat in an environment where they make them where they have no visual clues versus a lot of cues. So that's an active area in research, and they think a lot about how we can use some of, like, for example, the bat wing design and not wing, ear design compared to an owl, because owls also use, similar, and how and that's actually very powerful when you do bio-inspired design, is not to look at one thing that does something well, to look at a bunch of things that do the same thing, because then you can get out of it the feature that's really important, because what you see might be because of many reasons in biology. So they do comparative studies.
Thank you.
No problem. Please turn my
Thank you. First, thank you for the presentation. I often forget and take for granted nature in general, so it was great to be reminded of how wondrous and amazing this world is. And my question was going back to the flying fish. I was just curious, what about the asymmetric tail shape and its engagement with a wave would make it have that bundle effect that is almost more effective in a sense, I guess, than the symmetric?
That's a very good question. We actually found, because of how the water is flowing over the symmetric fin, basically, if, let's say, the water is in line with the fin like this, because it's symmetric, most of the momentum that gets, basically the fin is flapping, most of the momentum goes in this direction. So it helps with thrust. But once you start changing the depth, you really, you lose how much of that momentum. For the asymmetric fin, because it's long like that, vortices get shed at different times from the top and the bottom, and they interact with one another. And even if the fish is completely in parallel with the surface, there's a component of that momentum that's basically injected down, convected downwards in the flow, and equal and opposite is basically lift. So even though, and then in taxiing, a component of that becomes also in the thrust direction. So as you're changing the depth, because of this asymmetry between when the vortices are shed and how, you always can maintain a component in the thrust direction.
Thank you.
No, thank you. Very good question. Yes.
I have another question about the flying fish. Are there wings, airfoils, or are they flat?
Such a good question. Okay, I can't do it now. Okay, they are mainly flat. They're mainly flat. But if you actually look at the bottom of them, there's rays that give them stiffness, like basically stiffen them up, kind of like think of them as the bones in a bat wing. And that gives them so it's not smooth, but it's not smooth on the pressure on the bottom side. But it's mainly flat and a little cambered. So you can think of it as a very thin wing that's a little cambered. Yeah, no problem.
Like how you showed how the click beetles were able to jump by using the latch and then loading, and I was wondering if grasshoppers do the same thing.
They do. So grasshopper has a latch-mediated spring actually in their legs that allows them to jump. So they have and it's actually such a good question. They have the same strategy of latch and springs, but their latch is not about geometry. Like there's no two surfaces that come in contact and they look the same. They use lever arms. So there's a lever arm. Think of it like a seesaw, and some for a certain level of energy storage, it doesn't move. But once you pass the fulcrum, then it snaps. So, but yes, they do, and they have it in their legs, and people study them and a lot to think about what's the latch, what's the spring, and it's been helping them with their jump. So it's fleas.
Thank
Good
you.
question. No problem. There's actual grasshopper down here too if you want to look at it later. Hi, yes.
Two questions if you don't mind. My first one is if the pectoral fins on the flying fish are used for both swimming and flying, what are the lower fins used for?
Oh, sure. So the pectoral fins are used during flying, they're used as wings. During swimming, they're used a lot for directional control, kind of like how other fishes use it. And then you're talking about the pelvic fin, like the one that's a little lower. It's actually interesting. Some species of flying fish have enlarged pelvic fins, some species don't. So some of them, they're called four-winged, and the bigger they are, they tend to have four wings. So their pectoral fins are enlarged, but their pelvic fins are enlarged, and they act like almost like four wings. And some of them, they don't need it. The smaller ones, they don't need it. And we found that if you have an enlarged pelvic fin, it helps also during gliding because it makes you stable, almost like a tail on a big airplane. It helps stabilize in flight. But during swimming, it also helps with stability and control under the water.
Second question, do you have a favorite, like flying or generally airborne creature?
Oh, they're all my kids. No, I'm just kidding. I mean, I am biased. The last part of like birds is my first love, and they're gonna stay my first love, no matter what other fish, insects crawl in the lab. And out of birds, I am in love with peregrine falcons. Just they're incredible as an inspiration for aircraft. Yeah, thank you for the question.
Thank you so much. I loved your talk very much. There's a lot of beauty in using engineering to understand the biology and then you taking those learnings to improve physical systems in engineering. And I'm wondering, like, I can imagine you're a part of multiple communities that care about different things and work with funding agencies that care about different things. And I'm wondering what you can say about your experience kind of working between and with multiple disciplines.
It's my favorite thing about what I do, and it's really hard. Like it took me a while. I had like I feel like I can share with you guys too much for some reason, but I had this existential crisis, right? Like, would engineers view me as engineer enough? Would biologists think I know enough of biology to be a biologist? And how do you talk? And it took a while. It took years to be able to show up to both communities and be able to appreciate the strength and where my contribution can fit in. So it was hard in the beginning. And now I'm enjoying it so much because I actually see a lot of this work is collaborative. You saw people's picture pop up and all. I was running behind time, but a lot of these are biologists. Some of them are engineers that do different things. And it's when we get together, a lot of the insights, sometimes as an engineer, and also the click beetles are perfect. I was so arrogant in the beginning. My colleague told me, can you help me model how this beetle jump? I'm like, it's not that hard. There's like a mass in the front, a mass in the back, and a little hinge in the middle. Give me like 10 minutes. Give me like a couple weeks and I can give you a model. And sure, my model worked in getting it to jump, but I had no idea about where's the energy coming from? How is it doing all that? And it was by working together. And she's like, well, your numbers don't make sense because muscles can't do that. So then we took back a step and we went to literature. So it's actually when you bring these communities together and when you collaborate with people that come with different perspective and different motivations, that's when the beauty of science shows. And it's really cool. The collaborations are really cool. Funding is actually pretty hard because if you talk to, NSF, for example, biology is in one building, in one part, and engineering in another part. But nicely in the last, few years, there's been a lot of programs that are getting into interdisciplinary science. So these are programs definitely targeted to saying, how can we bring biology and engineering? How can we bring engineering and psychology, engineering and art? So I'm really happy to see that. Yeah, thanks.
Oh, thank you very much. As a pilot, I'm very familiar with the fact that on the lift angle of attack curve, the lift really drops off at the critical angle of attack. Now, are your ideas about reducing that drop off of lift being applied to aircraft manufacturers right now? Are they looking at this kind of thing?
So this study that shows completely like we suppressed stall completely just came last year, and since then there has been a lot of interest of companies, and one of the big question they have the Reynolds number, so that's the speed and the scale I tested in is very relevant to birds, and the big question is this scalable for bigger systems? So we're actually now talking with a big research institute in Germany and here in the US to put these systems on bigger test airplanes to see how much is scalable and what materials would we make it from and how much would be disruptive to pre-stall. So yeah, we're thinking about it now so I'm excited to see that. We'll see what happens, but yeah, it's exciting.
There's a question in the back to your right.
Sure.
Yeah, thank you. A very great talk, and I enjoyed a lot. And so you mentioned that the beetles can jump about like 20 times of its length of the body. So I was just wondering, your robotic beetle, how is the performance?
So very, very nice question. So the smaller beetles can do 20 times their body length. The bigger beetles can maybe do 1 or 2. Ours is about 0.81. So it's very close to beetles. It's not that far from the realm of beetles of their size, but we are a lot heavier still, and that's something we're thinking about because the lighter we can make our whole system, then the higher the jump. But where our scale is as close to the bigger beetles, and our jump is still not as good as them, and I think but there's room for improvement in terms of we have a lot of room to improve in terms of mass. But yes, thank you.
TK, right here.
Yeah, thank you. I have going off to a tangent. What is your definition of motion?
Oh.
And by that definition, is there anything in nature, any entity in nature that's not in motion?
The answer to that question is no. I think, okay, for my research, the definition of motion is kinematics. So displacements, velocity, accelerations. Now, I think if you take that definition and you think on a cellular level, a cell has motion, right? It's internal. In my definition, we're thinking about local motion. So it's the ability of a system to go from point A to point B. That's what we're studying. But motion in its absolute sense, the idea of that there's displacements and velocity acceleration, you can measure that at the microscopic nanoscale of cells moving and nutrients moving and within muscles even. So I think a very broad definition of motion, I think then everything is, I would say everything is in motion. But for our things, we're thinking more about locomotion. So an animal or an organism ability to move from point A to point B and the physics that enables it to do that.
So by that, would you say that the trees have no motion?
Well, no. I think if you look at a tree, if I think about the tree, the way it's moving nutrients, I think that you can call that motion. The way the branches are moving, that's motion. But I would not quantify that as locomotion.
Thank you.
No problem.
Thank you. The fish, it appeared that the lower fin is longer than the upper one.
Yes.
Have you done an experiment where you switch those and see if that works or doesn't work? Or
Yeah. So when so sharks have the flip where the top is longer than the bottom. And my collaborator actually studies also shark species. And we found that the opposite happens. The way if you have the dorsal fin or the top fin lower than bigger than the bottom one, again, it creates this different time. It creates this asymmetry in when the vortices are shed. But the direction of the momentum is, the idea would help it stay down, not up. Yeah, because of the downwash and how it's shed. Yes.
I have a question about the kite experiments that you did, and presumably you go up high so you get the good winds for energy.
Yes.
And I presume somehow that energy is transmitted back to useful energy by the kite string.
Yes.
And how is that actually done?
So
how do you get energy out of that?
The way they do this, I can share my screen again. The way they do it is not by harvesting the energy. Maybe from current slide, would this work? Oh, they're actually, so maybe I can share my screen real quick. I think it's worth showing that. I don't know where my Zoom went. Oh, here it is. Okay, share. Okay, here we go. Okay, so there's actually a generator on the ground, and the string is tied to the kite. And then what happens is, what you see in blue here is they're doing this crosswind figure 8 maneuver, and the generator is producing power. And then they have this, and it's called the reel out. And then there's a reel in, and that's the red. And in that, they try to go with the least drag and reset that again. And the net between reel out and reel in is the net power. They have wind, they have like little propellers on board for wind, for power generation, but they use that just to power sensors. Now, the big question with this concept, they went up to 5,000, they're up to 3,900 meters now. They have net power generation. The question is, how heavy is that string when you get to the heights they want to get to, and how feasible that will become? So they have this vision, and we're working with them so all these things to increase lift ability, increase payload ability, hopefully is helpful. But for the first phase of the project, we just wanted to showcase that our control effectors can do this figure 8 in a controllable manner. Yeah, they call it the pumping cycle. That was the other video that didn't work, but yes. Yeah, here it is. Here it is with the kite doing it. So yeah, so we figure 8. Yeah, yep. And you align to the crosswind so that you can get the most wind. So, yeah. No problem. Thank you.
Hi, yeah, thank you for your presentation. I was just curious if you're aware of anybody having like a physical model of bumblebee flight.
Yes. There's a RoboBee is an insect scale inspired by bees and out of Harvard, and they have been really successful. One in terms of getting the wing kinematics, in terms of generating the big bottleneck in insect scale robots, and this is something that we're starting to think about a lot. Is all these robots so far are tethered, because we don't, they're very energy expensive, and batteries are still too heavy to carry on something that's so small. So they're tethered. So in terms of power, that's the part that's a bottleneck. But in terms of success in producing lift, and actually the robot, they took versions of this robot and have it take off from the water, or they've been really cool. Like if you look up RoboBee videos, you can go down that road for a couple of days. It's pretty cool. Yes, no problem. Hi.
How do the beetles survive the 300 something Gs?
You and me, my friend, are no obsession. No, I think it's actually very interesting, and we're doing some now experiments where we're taking the beetle cuticle and we're looking at how the material properties. But we found very interesting, us and other people in mantis shrimp, we found very exciting things in terms of the architecture of their clubs, that it basically prevents crack propagation. So it's very strong in that way. The question that I am thinking about a lot is, where's this energy? How are they able to target all this energy towards moving and not towards where is it getting damped basically? And that is a completely open question. One of the researchers working in this field is thinking a lot of it actually goes in the muscle, because if you think about a muscle, you can think of a muscle as a piston, and it has like the kind of in the door when you open the door, and it helps you close down with the damping. We think muscles act like, they call it a dashpot. We think muscles have that property of damping a little bit, but this is a huge open question into this whole field. Where's the energy going? How is it damp, and how, but to be honest, the shrimp, the club of the shrimp, it actually gets damaged over time and they replace it. So some of them replace it, but as far as I know with the click beetles, we did many experiments and we're not seeing that much wear and tear in some of these elements. So it's an open question.
Thank you.
You're welcome.
Thank you for the talk. I was curious, we've seen models of kinematics at various scales. I was curious what the research is into modeling kinematic processes at the molecular level or protein level.
This would be me speaking completely outside my area of expertise. I am, to be I think the short answer is I'm not sure where is the the edge of knowledge in terms of that, but I know this is a really active, we have colleagues that really are actively thinking about on like the cellular level, how are cells growing and multiplying and dividing, how are they moving? There's many models and that people think about that, and but and some experiments that are trying to validate, which is I think one of the really hard part about when you start working in this scale, you want to try to validate some of this models that you come up with experiments, and with these systems on the molecular scale, and even some of our work, once you kind of measure it, sometimes you disrupt it so that your measurement is, so that's, I think that, I know that's an open question. Beyond that, I'll be making stuff up, and we've established that I like you guys too much to lie to you, so I don't want to do that. Yeah. Hi.
Hi, thank you very much. I learned a lot today. It's really awesome talk here. I found very amazing is from the research perspective, you're using very simple designs to really learn the very complex information here. That's really amazing. So what I want to know is, during the research, how much of computational modeling you leverage, right? Instead of just starting building devices look similar, right? As a start. Second question on top of that is how, for these days, how much of AI your team or your, how you want to implement it, if any. So that's my question.
This is both are very good questions. I think one of the to answer to your comment, and I think this is something that we have worked really hard in the lab to do intentionally, is to, with bio-inspired design, biology is super complex for many reasons, evolutionary baggage from ancestors, many reasons, right? So what the picture of biology that we see today is a result of millions of years of trial and error. So if you copy complex things, it becomes very hard to discern what's doing what, when, how. So a lot of the time we try to get at the simplest system that will give us the physics that we think is happening. So that's kind of the guiding principle. So sometimes we start with, the second part of the question of using computational, it depends. In some systems where, for example, for the flying, the Reynolds number, so the speed and the scale we're thinking about, as well as this high angle of attack maneuver, there are no models, CFD models, computational dynamics model, that would be able to handle all these scales. A lot of the models that are there are powerful, but they simplify. Either they solve all the scales, like I showed you in these videos, for example. And I know I'm taking too much. I have nothing else to do today, so I'm here. But I understand if I'm talking too much. All right. So this video right here, if it plays, you're seeing a lot of scales, big things turning, little things turning. So, and we can't even, and there are a lot of things in the wall. So there are no computational models that are able to resolve all these scales. They either do it at much smaller scales, smaller Reynolds numbers, they can resolve everything, and that's really powerful, or they end up averaging these models. So in cases like this, experiments basically is kind of, I wouldn't say the only way, but one of the most faithful, most validated ways of thinking about this, because with models. In other parts of our scenarios, like with the click beetle, we started with a computer analytical model in like a coding where we put mass and enforced ballistic motion and did some analysis. My lab mainly focuses on analysis and experiments, but we collaborate with others to do computation. So when we did the flaps, I was working at this Reynolds number where experiments have the edge, and my colleague at University of Illinois Urbana-Champaign was working on a CFD, a computational fluid dynamics model, at a much smaller Reynolds number where computation had the edge, because you can see everything, and so we always work hand in hand. The AI question is a very interesting question. I have two ways of answering. The first one is to say, one of the powerful things of AI is that we're leveraging and we're thinking about is these experiments have huge parameter spaces. So where AI is really helpful is if you have data that has many parameter spaces, it can help you find patterns and think about that, and helps, there's a synthesis. One of the things that I worry about a lot is sometimes, often when you do the synthesis, you lose the physics and it becomes less interpretable. So I'm really, the conversation with AI in my lab is about how can we leverage it to understand the physics better, not how can we leverage it to basically substitute some of this really fundamental understanding of what the physics is. And I also think one of the other things, my other soapbox is, we got in trouble in robotics when we started thinking about actuators and sensors for everything. you want to move something, you need to sense it, and you need a controller, an actuator, and a sensor. And we basically made the structure a dummy, where nature is teaching us the structure itself has properties that you can leverage. So a lot of this, I call that mechanical intelligence, not me, like our whole field that calls it. So I leverage a lot of mechanical intelligence before I start thinking about artificial or computational intelligence. Because if you think about your body, and how it moves, you're responding at many different levels to disturbances before your brain even gets engaged. So
Great. Thanks a lot. It's really amazing. Appreciate it.
Thanks.
Hi. I'm just curious. This Air Force has a fighter called Raptor, F-22.
Yes.
So does the fighter really fly like a Raptor?
Does it flies like a raptor? Does the F-22 fly like a raptor?
Yeah, they are named after.
Oh,
Raptor.
yes. No,
So what do you think?
I think it gives us raptor feelings, but the physics is very different. So the Raptors and F-22, F-35, I used to do my graduate student ride at NASA Langley, and we had an Air Force ride, so we would see F-22s flying all the time, and they're amazing, amazing machines. I think they're flying, the physics that they're leveraging is similar and different in some sense, in terms of they're much higher speeds, they're trying to do these large maneuvers, they have these really sophisticated controllers on board that, so it's flying unstable, it's almost at the margin of stability. Some of these aspects birds share in terms of, leveraging stability and maneuverability, these big fast dives. But again, where I think what some of the things that birds do, Raptor F-22s don't do, like staying up for hours and hours and hours and conserving energy and being super aerodynamic efficient. And some things that raptors do, birds don't do. So I think it just gives you a feeling of being I think the name is all about creating feelings rather than copying the physics, in my opinion.
So
But,
should Lockheed Martin come to talk to you?
Well, they can, if they want to design, yeah, they can. I mean, I would like to talk to them, and I wouldn't be criticizing the F-22. I'd be like, let's make something that, leverages the actual Raptor to do some different things. Yes.
I think we have time for the last two questions.
Perfect.
So I had a question. Well, firstly, very good talk. I enjoyed it very much.
Thank you. Appreciate it.
But you mentioned that the biggest strength of the smaller scale animals in terms of acceleration and explosiveness is due to their size.
Yes.
And also, as you mentioned, the spring-like qualities that are latching mechanisms. But I also wondered, do the exoskeletal properties of the actual structure have their own advantages versus mammalian skeleton properties?
Yes. So if you think about, actually, I think the cuticle, so in the insect world, that's called the cuticle because, they're invertebrates. But so the cuticle of the insect, it plays a huge role. I think there are and it's actually one of the most new areas of opportunities for us to understand. I think there's a lot of little springs that are built into that cuticle, ways of targeting the energy and moving it around. So it plays a huge role. With something else that we think a lot about with the grasshopper, the way insects kind of evolve and grow, everything comes from this basically one membrane. And then things come, so the formation, how does it form? How does things harden? And which ones harden and how they harden actually plays a huge role in all the behaviors we see. So it's a very important role that those cuticle and cuticle structure play.
Thank you.
Yes, no problem. Very good question.
This time I know how to use the mic.
I heard you the first time.
Okay. You were talking about the NSF and that the NSF has trouble with two different locations for biology and for engineering. I'm thinking when you're doing these integrative works, that it might be another department you wanted to bring in too. So part of what I'm interested in is if the world was more progressive and could give you more opportunity to have another department, for example, interfacing with you, and you applied what you were doing to prosthetics, and not just prosthetics, but perhaps prosthetics that can do different things than a hand or foot could do because of imagination. I wondered if you'd address that.
So to the first point, I think there has been a lot of efforts at NSF and other places to create interdisciplinary programs. So we just got funding from NSF because they have this whole program called the RAISE, which is research in interdisciplinary areas, and it's the only fund in interdisciplinary work, and you have to convince two scientists in two different fields that you need those two fields to be able to answer this research question. So that's happening, which is interesting. There is a lot of work in prosthetics and human biomechanics. A lot of this work is in animal biomechanics. I think there are features in it that could be applied to the design of prosthetics and wearable devices, like, energy and using, rather than have these big bulky motors and things. And people are thinking about that. And usually that's under them. There are programs that are solely focused on human biomechanics. So those are things that, for example, some of our work would not fit in. But yeah, but it is, and I think.
But I think the way you're approaching it in terms of imagination and creativity.
I think so, and I think that's something that's actually something that we think about a lot in terms of the field of like I have a student who's got ready to graduate. She's the one who's been working on the click beetle project, and she wants to work on prosthetics. And one of the conversations we're having right now is how can we make your work attractive to a company that's trying to hire somebody? And it's actually a challenge because a lot of times people are thinking, have you worked in human biomechanics? Great, come work on human biomechanics. And that translation, even in terms of careers, even though some of the tools, skills, and methods are translation. So it's a real challenge, but it's an opportunity also for us to do, to think about how to transfer methods versus like systems. Like if you're a beetle person, you're always a beetle person. I started working with plates, like I told you guys, and then I end up getting into airplanes. And then now I'm thinking about all that just because in academia, we have this freedom of exploring things, but that doesn't translate sometimes outside the academic landscape.
And I just noticed today that not only did you inspire and motivate and make happy the older population, but the ability of the young people to ask questions. Simply extraordinary. This was a great time. Thank you.
I appreciate that. I think I like you guys all, but the younger people that are here are like makes my heart happy. So thank you so much.
Thank you, Professor.